In all these types of questions, what we're looking to do is work with the sum and product of the roots without actually knowing what the roots are. But we do know from previous proofs that alpha plus beta is equal to minus b on a. We do know that alpha times beta is equal to c on a. We know that from our quadratic, a is equal to 1, b is equal to minus 3, c is equal to minus 5. So what we can do is, once we've got those values, we can do some substitution. Alpha plus beta would equal minus b over a. Do the substitution. The sum of the roots is 3. Do a substitution of c, which is minus 5, which gives us the product being minus 5. So we've found the sum and the product of the roots without actually finding the roots. All the rest of the question, we were working with the roots, but we don't know what the roots are. But we can, as long as we can get down to the product or sum, we can work the question out. So expand our brackets as we normally would, gives us alpha times beta. There's our product of the roots. Alpha plus beta is almost there, but if we factorise 4 out, there we go. We have the sum of the roots, which we know is 3. We know the product is minus 5. We can do our calculation now, and alpha plus 4 times beta plus 4 is equal to 23. We didn't know what the roots were, but we can do that calculation. The next question, again, we've got alphas and betas in there, but how can we get alpha times beta? Well, we can factorise it out. It's a simple factorisation, and that leaves us nicely alpha plus beta in the brackets. Now, this has been swapped around a little bit. We know alpha times beta is equal to minus 5, and alpha plus beta is equal to 3, but it was multiplication there, so it doesn't matter. 3 times the minus 5 gives us minus 15 for that expression. This time we've got fractions. Now, when we have to add two fractions, we need to find a common denominator. Nicely, our common denominator works out to be the product of the roots. We have to get our common denominators, but then our numerators, we have to do some multiplication. Gives us beta plus alpha, same as alpha plus beta, which is the product sum of the roots, which gives us 3. That comes down to nicely minus 3 on 5. Everything's coming back to alpha plus beta or alpha times beta. This is one of the harder ones, because we have to manipulate alpha squared plus beta squared. But if you have a look down here at this manipulation, if you remember our expansion of our a plus b all squared would equal a squared plus 2ab plus b squared. But then if we subtract 2ab off on either side, that leaves us with a squared plus b squared is equal to a plus b all squared minus 2ab. This part just got subtracted. Then, if that's the case, what we can do is say that alpha squared plus beta squared is equal to alpha plus beta all squared minus 2 alpha beta. Now we've got the product of the roots in there, and we've got the sum of the roots in there. We can do our substitutions, and we're able to simplify it. As long as we can get back to the sum of the roots and the product of the roots, we can always work them out. Also, if we have this situation, we look at what we've got. Again, two fractions, have to add them. Common denominator would be alpha beta. Alpha times alpha gives us alpha squared. Beta times beta gives us beta squared. From our previous part, we know that alpha squared plus beta squared gave us 19. Alpha times beta is minus 5, and it comes down to minus 3 and 4/5. And the final part here, we have to expand our brackets. Alpha times beta is alpha beta. Alpha times 1 over alpha, that multiplies just to give us 1. 1 over beta times beta gives us 1 again. And 1 on beta times 1 on alpha gives us 1 on alpha beta. Product of the roots, do our substitution, throw it into the calculator to give us minus 7 and 1/5. Notice with every question, it comes down to alpha times beta and alpha plus beta, because that's what we've got values for, and that's what you've got to try and find every time.